welcome back to the deep dive. If you've ever had an MRI scan, you know it provides incredible details about your soft tissue, your brain, your knee, ligaments, stuff that no X-ray or CT scan could ever really hope to match.
Absolutely. The level of detail is just phenomenal.
But have you ever stopped to think where that stunning high-resolution map actually comes from? I mean, what's the real magic behind turning the tiny quantum spin of a proton into a detailed image we can actually use? It's got to be more than just a big magnet.
Oh, it's much more. And that complex physics, it all gets synthesized really in this hidden conceptual data map. It's called K-space.
K-space, right.
So today we're really going to dive deep into this non-physical, multi-dimensional grid that basically defines almost every decision an MRI scanner makes.
Okay.
Our mission, if you like, is to trace the whole journey from the basic magnetic principles that give us a signal in the first place, through the tools, the spatial encoding that locates that signal, all the way to how, cutting-edge AI is now designing the optimal path through K-space.
To make it faster and better quality.
Exactly. Maximizing efficiency and image quality. We've looked at everything from core physics texts to brand new research papers on using neural networks for this.
Okay, fantastic. So let's unpack this, starting with the star of the show, right? The proton. If you, the listener, know a bit about this, MRI works because our bodies are mostly water and fat.
Yep.
And both are just loaded with hydrogen nuclei, which are basically single protons.
That's the absolute starting point. Each one of these protons, it acts like a tiny, tiny bar magnet.
Right.
But normally, outside the scanner, they're all pointing in random directions. Just complete chaos.
So they cancel each other out.
They cancel each other out, exactly.
Yeah.
The net result is zero overall magnetism, nothing to measure.
Then we slide the patient into the scanner, into that huge tube. That's the main magnetic field, the B-dollar.
That's the big one. B-dollars in hospitals is typically, 1.5 Tesla, maybe 3 Tesla? Research systems push it way higher, though. We're talking up to 9.4 Tesla for human imaging now.
Wow. That's powerful.
The sheer power of B-dollars is, it's immense. And it does two main things to those protons. First, it forces a tiny, tiny majority of them to line up, roughly parallel to the direction of that main field.
Just a tiny fraction.
A very small fraction, but it's enough. This slight surplus alignment creates a measurable, sort of large-scale net magnetization. We call that dollar.
Okay.
And dollar is the foundation. That's the signal we're going to work with.
But, okay, so this net magnetization of dollars just sitting there, aligned with B-dollars, how do we actually get it to, produce a signal that our receiver coil can pick up?
Right. We need to make it talk to us. We use the phenomenon of magnetic resonance. See, the magnetization dollar, it doesn't just sit still. It actually spins or precesses around the B-dollar axis, kind of like a spinning top does.
Okay, like a wobble.
Exactly like a wobble. Now, to get a signal, we need to inject energy at exactly the right frequency to match that wobble, that precession rate. Its characteristic resonant frequency, $.
And this relationship, this is key for knowing where things are later on, right?
Right.
It's governed by the Larmor equation.
Precisely. The Larmor equation is really the bedrock of MRI physics. It's $, gamma, B-dollar.
Omega equals gamma B 0.
Yeah. And what's critical here is the direct proportionality. The precession frequency, $, is directly tied to the magnetic field strength, B-dollars. That constant gamma is just a physical property of the proton, the gyromagnetic ratio.
So the stronger the field, the faster the wobble.
Exactly. The equation tells us the precise radio frequency, the RF, we need to pump in to excite these spins.
Okay, so we have $me aligned along the dollars. We know the frequency from Larmor. We then fire this excitation pulse, the B-dollar field, at that frequency.
Yep. That $1 pulse is like a perfectly tuned wave of energy, and its job is to tip that net magnetization $11 away from the main field direction.
Tip it over.
Tip it over. To help visualize this, think of a coordinate system. $. Is always along the z-axis by convention.
Okay, Z is up.
So when the protons align with $, that's the longitudinal magnetization. It's along Z.
Right. So what happens to that longitudinal bit when we hit it with the RF pulse?
That pulse transfers energy, and it essentially knocks the magnetization vector out of the z-axis and down into the xy plane.
Okay.
That portion of dollars that's now perpendicular to $, lying in the xy plane, that's the transverse magnetization.
And that's the signal we measure.
That's the signal. Because it's rotating in the xy plane, it induces a tiny electrical current in our receiver coils. If we can't tip it into that transverse plane, we get absolutely zero signal.
Got it. And then, once we switch off that excitation pulse, the $1,
Yeah.
the party's over, right? The system starts to kind of wind down?
That winding down process is called relaxation. The transverse signal, the one we measure, it starts to decay, and the longitudinal magnetization starts to recover, growing back towards its alignment with B dollars.
And it doesn't happen instantly.
No, and crucially, the speed of this relaxation, both the decay and the recovery, it happens at different rates depending on the local chemical environment, basically the tissue itself.
Ah, okay. And this is where MRI gets its amazing contrast between different soft tissues.
Absolutely, that's the secret sauce. The characteristic time constants, we call them T dollars for the longitudinal recovery and $2 for the transverse decay. These are like tissue signatures.
Signatures, okay.
For example, fat recovers its longitudinal magnetization quickly, so it has a short T-Taller winner. Water or fluid recovers slowly, long T-Taller winners.
I see.
This difference allows us to design specific pulse sequences, things like spin echo or gradient echo sequences, that specifically emphasize these T-Taller or T-Taller 2 differences. That's how we get that stunning contrast between, say, gray matter, white matter, cerebrospinal fluid, or even tumors. MRI isn't just mapping where protons are, it's mapping how they behave in their specific neighborhood.
Okay, so we've established we have a good signal,
Okay.
and it's tissue-specific because of relaxation. But right now, it's just one signal coming from the whole slice or volume we excited, isn't it?
That's right. If we only had the main B-dollar field, even with the excitation, we'd get a signal, but we wouldn't know if it came from your forehead or your chin. It's all mixed together.
We need the location. We need spatial encoding.
Location, location, location. Exactly.
Yes.
And the way we get that is by, well, intentionally messing up the beautiful homogeneity of the main B-dollar field.
Messing it up. How?
Instead of the Larmor frequency being the same everywhere inside the magnet, we deliberately make the magnetic field strength B-dollar slightly different at different places within the patient.
And we do that using gradient coils.
Precisely. These are another set of coils, resistive electromagnets, inside the scanner bore. And they can rapidly switch on and off to create a linear variation, a slope in the magnetic field across the imaging volume.
A slope in the field strength.
Yeah, think of it like a ramp. We can make the field slightly stronger on the left and slightly weaker on the right, for instance. These gradients are measured in units like millitesla per meter, say 20 to 100 millitimeter.
Okay, so if we turn on a gradient, say along the y-axis,
Then the total magnetic field B-dollar experienced by a proton now depends on its y position. And according to our friend the Larmor equation, if B-dollar changes with position, then the precession frequency, a megadollar, also changes with position.
so spins at different y locations will now precess at slightly different speeds.
You got it. That's the absolute heart of spatial decoding. We're using frequency and phase, which depend on field strength, to label position.
And you mentioned the scanner noise earlier, that loud banging.
Yeah.
It's these gradient coils switching.
That's exactly what it is.
Yeah.
Lamax, the maximum slew rate, that's how fast we can ramp the gradients up and down. Dmax is how strong they can be. To map things quickly, we have to switch these powerful gradients incredibly fast.
Wow.
That rapid switching causes the coils to physically vibrate against their mountings due to the huge magnetic forces involved. And that vibration creates the loud acoustic noise the patient hears. So yeah, faster scanning often means louder scanning. It's the sound of charting K-space at high speed.
That makes so much sense. Okay, so we use two main tricks then for encoding in 2D or 3D. Phase encoding and frequency encoding. Let's talk phase encoding first.
Right.
Usually y-axis.
Usually Y, yeah. Phase encoding is, well, it's quite clever. We turn on a gradient along Y for just a very short, precisely controlled amount of time. Okay.
Now, during that short pulse, spins at different y locations precess at different speeds. So they start to get out of sync with each other. They accumulate a phase difference that depends on their y position.
They drift apart in their rotation angle.
Exactly. Then we switch the gradient off. Now all the spins go back to precessing at the standard Larmor frequency determined by B$Lawlers. But that phase difference they accumulated, it sticks.
It persists, like a memory.
It persists. It acts as a memory of their y-axis location during that brief gradient pulse.
Okay, that's neat. But how does that give us the whole picture?
Well, here's the catch. That only gives us one level of phase information. To build up the whole image along the y direction, the machine has to repeat the entire process, excitation, phase encoding gradient, readout many times. And each time, it applies a different strength or duration of the phase encoding gradient.
So it steps through different amounts of phase shift. Exactly. It applies a weak gradient, gets a line of data, then a slightly stronger one gets another line, then stronger still. It needs to do this for every single line of data it wants to collect in that y dimension, say 256 times for a typical image.
And each repetition takes time. The TR, the repetition time.
Bingo. And that is the primary reason why standard high-resolution MRI scans take minutes, not seconds. Filling up all those phase encoding steps just takes time.
Okay, I see. That explains the duration.
Yeah.
Now, what about frequency encoding? The readout gradient usually along X.
Right. The frequency encoding gradient is different because it's turned on while we are actually listening to the signal during the readout period.
Okay, simultaneous measurement.
Yeah. So while this X gradient is on, spins at different X locations are forced to precess at different frequencies. The receiver coil picks up this incredibly complex signal, which is actually a mixture of all these different frequencies simultaneously.
Like a musical chord with lots of notes playing at once.
That's a great analogy. And just like our ear and brain can pick out the individual notes in a chord, we use a mathematical tool called the Fourier transform to decompose that complex radio wave signal into its individual frequency components.
And each frequency corresponds to a specific X location.
Precisely. The Fourier transform tells us how much signal came from each frequency, which directly tells us how much signal came from each X position.
Wow. Okay, so phase encoding for Y, frequency encoding for X, and all this spatially encoded data. It doesn't go straight to an image, does it? It goes into this thing called K-space.
Exactly. K-space is the destination for all this raw data. It's a matrix, usually 2D or 3D, filled with complex numbers that have both magnitude and phase. It was formalized independently by Lundgren and Twigg back in '83. It's the data before you do the final inverse Fourier transform to get the image you actually look at.
And the connection between the gradients we apply and where we land in this K-space matrix, it's direct.
It's incredibly direct and elegant. The position vector in K-space, let's call it vec, is literally the time integral of the gradient vector that you applied up to that time 2 events.
So KK gamma gam GDT, that equation pops up a lot.
It does. It basically says that by controlling the strength and duration of our gradients over time, the MRI machine is physically steering its sampling point through this conceptual K-space.
You described K-space earlier as a landscape. High mountains in the center, flattening out to a hazy plain. Can you elaborate on that? What does a single point in K-space actually represent? Is it a pixel?
No, and this is probably the most crucial and maybe counterintuitive concept. A single point in K-space does not correspond to a single pixel in the final image. K-space represents spatial frequencies.
Spatial frequencies, like how rapidly things change across the image.
Exactly. Low spatial frequencies represent the broad, smooth areas, the overall shape and brightness variations. High spatial frequencies represent the sharp edges, the fine details, the textures.
Okay, so every point in K-space contributes information to the entire image.
Yes. Every single point. It's not like a photograph where this part of the sensor captures that part of the scene. It's fundamentally non-local.
That sounds almost like a hologram, where even a small piece contains information about the whole thing.
That's an excellent analogy. It absolutely behaves like a hologram in that sense. The information is distributed. If you were to, say, lose a chunk of data from K-space, you wouldn't lose a corresponding chunk of the image. Instead, the entire image might become slightly blurred or have some artifacts, but you'd still see the whole structure.
Wow.
This inherent redundancy, this non-local nature, is precisely why modern techniques like parallel imaging and compressed sensing work. They intentionally don't sample all of K-space. They grab strategic bits and rely on that holographic property and clever math to reconstruct the full image anyway. It saves a huge amount of time.
Okay, that's fascinating. So if the information is spread everywhere, why did you describe the center of K-space as high mountains? Why is it so bright or strong there?
Because the center of K-space, the region around high dollars, corresponds to the lowest spatial frequencies. These frequencies carry the most signal energy and, critically, they determine the overall contrast of the image.
Contrast. So like the difference between gray matter and white matter or fluid and tissue.
Exactly. The fundamental grayscale values, the signal intensity differences between tissues, that information is primarily encoded in the center of K-space.
In the outer regions, the flat, hazy plane.
That's where the high spatial frequencies live. This data defines the resolution, the fine details, the sharp edges, the borders between structures.
So there's a trade-off.
A fundamental trade-off. If you don't sample the center of K-space well, your image will be washed out, lacking contrast, even if it looks sharp. If you don't sample a periphery well, your image might have great contrast, but it will be blurry, lacking detail. Getting the balance right is key to a good image.
Right, so the moment we do that initial excitation pulse, the clock starts ticking, the signal begins to decay. Our job as the cartographer of K-space is to fly our easily maneuverable rocket, as the source put it, over this landscape.
And record enough data points, enough signal height before it all fades away into noise. And since K, we always start at the center.
The path we take through K-space, the trajectory, is therefore critical, isn't it?
Absolutely critical. And it's under the experimenter's control. The most standard method, the one we implicitly discussed with phase and frequency encoding, is Fourier transform imaging. It uses a rectangular Cartesian grid, row by row or column by column.
Like reading a book.
Pretty much. It's the most common because it lines up perfectly with that phase frequency encoding logic, and it's ideal for using the fast Fourier transform or FFT algorithm for reconstruction, which is computationally very efficient.
But you mentioned it's multi-shot. We have to repeat the excitation pulse many times to fill that grid. That takes time. Are there faster ways?
Yes, the need for speed drove the development of other trajectories. One important one is spiral imaging.
Spiral. So it literally spirals outwards.
It literally spirals out from the center of K-space, usually in a single continuous shot after one excitation.
One shot. That sounds much faster.
It is much faster. And because the path is smooth, just curving gently, it puts less demand on the gradient system compared to the sharp turns and stops needed for Cartesian scanning. This can mean less acoustic noise, too.
And spiral has an advantage for contrast, you said.
It does, because it starts right at the center of K-space, where the signal is strongest and the contrast information lives. It captures that crucial data first, before significant signal decay, T22 decay, has happened. This tends to give it a good contrast and noise ratio, or CNR.
Okay, spiral is fast. But then there's a real speed demon, right? Echo, planar imaging, EPI.
Yeah.
You mentioned this is key for functional MRI.
EPI is the king of speed. It's also a single-shot technique, but its goal is to cover the entire K-space grid, or at least most of it, in just tens of milliseconds. Unbelievably fast.
How does it manage that? Does it spiral too?
No, EPI typically uses a zigzag or raster pattern. After the initial excitation, it uses a rapid train of gradient pulses that switch direction very quickly, sweeping back and forth across K-space, filling multiple lines in one go.
Tens of milliseconds. Why do you need to be that fast?
Because you want to capture dynamic processes. Think about functional MRI, fMRI. You're looking at changes in blood oxygenation in the brain, which happen on the order of seconds. You need to grab a whole brain image every, say, 2 or 3 seconds to see which areas are lighting up when someone performs a task.
Ah, okay. So you need a freeze motion, essentially.
Freeze physiological motion, exactly. EPI is the workhorse for fMRI, diffusion tensor imaging, DTI, cardiac imaging sometimes, anything where the anatomy or physiology is changing rapidly.
But there must be a downside to going that incredibly fast, right? Pushing the gradients that hard.
Absolutely. That breakneck speed and rapid gradient switching make EPI highly sensitive to any imperfections. It's very susceptible to 2-to-2 decay effects, magnetic field inhomogeneities, and chemical shift artifacts.
Leading to image problems.
Yes. The most notorious is ghosting, where you get faint copies of the image shifted in the phase encoding direction. It can also suffer from geometric distortions, especially near air tissue interfaces like the sinuses. It's a trade-off. Incredible speed for potentially lower image fidelity compared to slower methods.
Okay, let's back up a bit and talk about the echoes themselves. We get the signal back as an echo. You mentioned gradient echo, GRE, that involves reversing the gradient.
That's the simpler one. With a gradient echo, we first apply a gradient pulse, say along the frequency encoding axis. This causes the spins to get out of phase with each other. Faster spins get ahead, slower ones lag behind. Our trajectory moves away from the K-space center.
They dephase.
They dephase. Then we simply apply another gradient pulse with the opposite polarity, the opposite sign. This makes the previously faster spins slow down and the slower spins speed up relative to each other.
So they come back together.
They come back together perfectly. They rephase, producing a peak in the signal that's a gradient echo. It happens when the area under the rephasing gradient lobe exactly cancels the area under the dephasing lobe. Our trajectory flies back towards the K-space center. Think of runners on a track. They spread out, but if you instantly reverse the direction of the track, they'll all cross the start line together again.
Okay, simple gradient reversal. But then there's the spin echo, sometimes called Hahn echo. That uses a 180-degree RF pulse instead of reversing the gradient. Why is that 180 pulse so special, so much more powerful, you said?
This is a really critical distinction, fundamental to MRI contrast and diagnostics. The 180 cert refocusing pulse used in a spin echo sequence is genius because it compensates for signal loss caused by magnetic field inhomogeneity.
Field inhomogeneity, you mean the main B-dollar field isn't perfectly uniform across the patient?
Exactly. No magnet is perfect. Plus, the patient's own body distorts the field slightly. So even within the same tissue type, spins in slightly different locations will experience slightly different local magnetic fields.
And therefore precess at slightly different speeds, even without a gradient.
Precisely. This causes them to dephase and the signal to decay faster than it should, based purely on the tissue's intrinsic properties. This extra decay rate is what we call 222. So 222 is always shorter than the true intrinsic 222.
Okay, so how does the 180 pulse fix this?
The 180 pulse performs a magic trick. Imagine you have fast spins and slow spins dephasing. The 180 pulse effectively flips their positions in the race. The fast ones that were ahead are now behind but still moving fast. The slow ones that were behind are now ahead but still moving slow.
It swaps them.
It swaps their relative phase positions. Now, because the fast ones are behind and the slow ones are ahead, they naturally converge and come back into phase at a specific time point, the echo time, TE. Crucially, this rephasing works regardless of whether the speed difference was caused by an applied gradient or by static field inhomogeneity.
Wow, so it cancels out the effect of the imperfect magnet.
It cancels out the dephasing caused by static field variations. Gradient echoes can only rephase the dephasing caused by the gradients themselves. They cannot correct for the underlying T-2 decay from field inhomogeneity.
And that's huge for diagnosis.
It's massive. Because the spin echo removes the influence of the magnet's imperfections, the signal decay we measure depends only on the true, intrinsic T-2 relaxation time of the tissue and things like diffusion. T-2 is much more specific to the tissue's molecular environment. That's why T-2 weighted spin echo images are the gold standard for seeing things like MS lesions, edema, or subtle tissue changes. Gradient echo images, T-2 weighted, are more sensitive to things like iron deposits or susceptibility artifacts, but the contrast is muddled by the field effect.
Right, the tyranny of time. That phrase really captures the core challenge here, doesn't it? We're in this constant race against that signal decay, that T-tel to T-K, quantified by $2 and $2.
Which means our beautiful K-space landscape, those mountains of signal, they're constantly, relentlessly flattening out into that dull plane of noise.
Leaving very little time to spare for our cartographer.
Exactly. And this is why how densely we sample and how we control noise becomes so incredibly important. That 2-2 decay, which, as we said, is often dominated by field inhomogeneity, forces us to acquire the data quickly. If we take too long, especially getting out to the edges of K-space,
The high-frequency details.
those high-frequency details will be so weak, maybe already decayed down below the level of the background electronic noise from the receiver system.
Game over for resolution.
Game over for resolution. Now, if we happen to know the decay rate, R2 ever, and we know exactly when each K-space point was acquired.
Can't we just mathematically correct for the decay? Like boost the signal back up? The formula was QK, cropto QK. Right. Multiply the measured data by this exponential factor.
You can try. It sounds simple. Just apply the inverse decay factor. But here's the massive catch, the huge caveat. That correction factor, exponentially, it grows exponentially with time. So yes, you're boosting the decayed signal from the later time points, but you are also simultaneously exponentially amplifying whatever receiver noise was present in that measurement.
Ah. So you boost the signal, but you boost the noise even more.
You boost the noise exponentially right along with it. If you try to push this correction too far, especially for data acquired late in the readout when $2 is large, the amplified noise can just completely swamp the signal. You might reduce the blurring artifact from the decay itself, but you end up with an image that's incredibly noisy, basically unusable. It's a dangerous game.
So, given that we're fighting decay and potentially amplifying noise, the inherent strength of the signal we start with must be critical. Which brings us to the signal-to-noise ratio, SNR.
SNR, the bedrock of image quality. It's simply the ratio of the strength of the MR signal we want, divided by the standard deviation of the background noise. Our goal in designing any MRI protocol is almost always to maximize this SNR, or at least get enough of it for the diagnostic task.
And the main ways we can influence SNR, the main levers we can pull, are voxel size and scan time.
Those are the big two, yeah. And they involve a crucial trade-off. Let's start with voxel volume. The amount of MR signal you get is directly proportional to the number of protons in your measurement volume, which is your voxel volume.
Makes sense. Bigger volume, more protons, more signal.
Exactly. So imagine you want super high resolution. You decide to shrink your voxel size, maybe from a standard $2 times 2 times 2 millimeters, down to a tiny $1 times 1 times a 1 millimeter.
Okay, much smaller voxel.
Much smaller. That's 1/8 of the original volume. So instantly, just by making that change, you've reduced your signal strength by a factor of 8. Your SNR drops by 8 times.
Ouch. An 8x hit to SNR. So
Right.
wanting more detail. How do we get that back?
Well, the other lever is scan time. Signal averaging helps improve SNR. If you scan for longer and average more signals, the noise tends to average out. But SNR only improves with the square root of the number of measurements, or the square root of scan time.
Swear it. Okay.
So to compensate for that 8-fold loss in SNR from shrinking the voxel, you need to increase the number of signal averages, and thus the scan time, by $82, which is 64 times.
A 64-fold increase in scan time, that's huge. That turns a 5-minute scan into over 5 hours.
Exactly. It's a staggering cost. And it highlights the fundamental clinical reality. Getting those beautiful isotropic $1 times 1 times a 1 millimeter images is really only practical for scanning small, static body parts where you absolutely need that detail, maybe the inner ear, or a specific joint, or a small lesion in the spine. Trying to do a whole brain or whole body scan with that resolution and maintain SNR would take an impractically prohibitively long time. Patients just can't stay still that long.
Not to mention the cost and throughput.
Right, and even with small voxels, you still have to worry about the partial volume effect.
Partial volume.
Even a tiny $1 times 1 times a 1 millimeter voxel might still contain a mixture of different tissue types, especially at boundaries. Like maybe it's got a bit of gray matter and a bit of white matter, or some muscle and some fat. The signal you get from that voxel is then an average, blurring the true anatomical boundary and potentially hiding very small abnormalities. It's another limitation of spatial resolution.
Okay, so SNR is king, but resolution costs time, or SNR. Now, beyond just noise and blur, the way we sample K-space can introduce very specific image artifacts too, right? Like if we try to speed things up by reducing the field of view, the FOV.
Yes, particularly if you reduce the FOV in the phase encoding direction, which is tempting because it means fewer phase encoding steps and thus a faster scan. But if the part of the body you're imaging is actually larger than that reduced
The
FOV,
bits outside get chopped off.
they don't just get chopped off. They wrap around and get superimposed on the other side of the image. This is called fold-over or aliasing. It happens because the sampling in K-space wasn't fine enough to distinguish signals coming from outside the intended FOV. It's a direct consequence of undersampling in the phase direction.
Okay, wraparound artifacts. What about problems with the hardware itself? You mentioned the gradient noise. Can electronic glitches cause artifacts?
Oh, definitely. One classic artifact is the crisscross or herringbone pattern. You see these dark or bright stripes running across the entire image.
Stripes across the whole image. What causes that?
It's usually caused by a single bad data point or a transient spike of electronic noise somewhere in the K-space data matrix. Maybe there was a brief glitch in a gradient amplifier, or some RF interference got into the receiver.
But why does one bad point in K-space cause stripes across the entire image? Shouldn't it just affect one pixel?
Because of that Fourier transform relationship again. Remember, K-space represents spatial frequencies. A single sharp spike at one location in frequency space mathematically transforms into a sine wave, a repeating pattern across all of image space.
Ah, like dropping a pebble in a pond makes ripples everywhere.
Exactly. If the spike is right at the center of K-space, 0 frequency, the wave or stripe would be very broad and fuzzy. If the spike is way out at the edge of K-space, high frequency, the resulting sine wave in the image has a high frequency too, meaning the stripes are sharp and closely spaced. The exact location of the spike in K-space determines the spacing and the angulation of those stripes in the final image.
That's incredible. You can literally diagnose a hardware problem by looking at the pattern of stripes. Let's bring in another term here. The point spread function, or PSF. How does that relate?
The PSF is a really useful concept for understanding image quality and artifacts. Think of it this way. If your object was just a single, infinitely small point of light, or signal, what would the image of that point look like after going through your whole MRI system and reconstruction? Ideally, it would still be a perfect point.
But in reality, it's not.
In reality, it gets blurred or spread out due to all the imperfections, limited resolution, decay, noise, motion artifacts. That resulting shape is the point spread function. The final image we see is mathematically equivalent to the true object convolved with or blurred by the system's PSF.
So artifacts are basically undesirable features in the PSF.
Exactly. If you have patient motion, which might randomly corrupt some phase encoding lines in K-space, the PSF gets smeared out, and that smearing appears across the entire image. The herringbone artifact we just discussed is a PSF that has strong, stripe-like side lobes due to that K-space spike. Analyzing the PSF helps us understand why the image looks the way it does, beyond just saying it's blurry or it's stripy.
Okay, and one last thing in this section. Sometimes we intentionally manipulate K-space data during reconstruction, something called apodization.
Yes, apodization is essentially applying a filter or a weighting function to the K-space data before the final Fourier transform. Typically, you multiply the K-space data by a function that smoothly tapers down towards the edges.
Why would you do that? You're throwing away the high-frequency detail.
You are reducing the contribution of the high-frequency detail, yes. The reason is usually to improve the SNR or suppress ringing artifacts, Gibbs ringing, that can happen near sharp edges. By downweighting the outer parts of K-space, which often contain more noise relative to signal, you get a smoother-looking image with less apparent noise.
So it's a trade-off again.
Mm-hmm.
Better SNR, maybe fewer artifacts, but at the cost of some sharpness or resolution.
Precisely. It's another tool in the toolbox to balance image quality characteristics. And interestingly, as we talked about with two-taught decay, just ignoring the decay during reconstruction effectively acts like an unintentional apodization function. The signal at the edges of K-space, acquired later, is naturally weaker due to decay, so it gets downweighted anyway, which inherently reduces the effective spatial resolution, especially for trajectories like spiral or EPI that spend more time acquiring peripheral data.
Okay, so we've wrestled with SNR, T2 decay, the time cost of resolution. These brutal realities really defined the limits of MRI for decades, didn't they? All those acquisition strategies we discussed, Cartesian, spiral, EPI, they were clever, but they were fixed patterns, heuristics designed by physicists.
Right, they were based on geometric intuition or computational convenience.
But the modern way to try and escape this tyranny of time, as we called it, is, well, it's to stop guessing the best path through K-space and start learning it using AI and deep learning.
That's absolutely the frontier now. We're moving beyond just undersampling those fixed patterns, which is what older acceleration techniques like parallel imaging or standard compressed sensing did.
Right, compressed sensing undersamples, maybe randomly, but usually along a predefined grid or radial lines.
Exactly. It assumes the pattern, then figures out how to reconstruct from the missing data. The new idea is, can the AI design a completely novel, non-standard K-space trajectory itself, tailored to the specific scan, to be maximally efficient for reconstruction with a deep learning network?
So the AI designs the path from scratch. How does that even work? One novel approach uses something called neural ordinary differential equations, neural ODEs. That sounds very abstract.
It is pretty abstract, but the core idea is dynamic optimization. Instead of thinking of the K-space trajectory of K-area as a fixed shape we draw, the system treats the process of acquiring K-space data over time as a dynamic system. Its state evolves according to some rules, an ordinary differential equation, ODE. A neural ODE then uses a neural network, a flexible function approximator, to learn the parameters of that ODE. Essentially, the neural network learns the underlying physics or rules that govern the optimal movement through K-space over time.
So it's not learning the final shape directly, but learning the velocity and acceleration commands needed to generate the best possible path.
That's a great way to put it. It learns the dynamics DGT2s that lead to the best final image, given constraints. And crucially, this is often done using a joint training strategy.
Joint training, meaning?
Meaning they train the neural ODE part, which learns the trajectory, at the same time as they train a deep learning reconstruction network, often a UNet or similar CNN, which takes the undersampled data from that trajectory and reconstructs the final image.
Why train them together? Why not learn the best path first, then train a reconstructor for it?
Because they learn to help each other. The trajectory learns to sample K-space in a way that specifically plays to the strengths of that particular UNet reconstructor. It learns which K-space points are most critical for that network to fill in the gaps effectively.
So the path might look weird to us, but it's optimized for what the reconstruction AI is good at inferring.
Exactly. The UNet, in turn, gets better at reconstructing images that come from the kinds of undersampling patterns the neural ODE likes to generate. They become co-adapted, synergistically maximizing performance under heavy undersampling.
Okay, but wait a second. If the AI trajectory is optimized purely to make that specific UNet happy, doesn't that create a potential problem? Like, have we baked in a bias? Is the raw data collected using this AI trajectory still useful if we wanted to try a different reconstruction algorithm later? Or have we lost something fundamental by letting the AI optimize the physics just for one specific downstream process?
That is an excellent question, and it's a major point of discussion in the field, the potential lack of generalizability and the black box nature of these learned trajectories. It's a real ethical and scientific challenge.
How do they address that? Do they just trust the AI?
Well, one absolutely critical step is to anchor the optimization in reality. The AI isn't allowed to just invent any crazy path it wants. The optimization process explicitly includes constraints based on the real-world physics of the MRI scanner hardware.
Ah, like the maximum gradient strength and slew rate we talked about earlier?
Yeah.
Gmax and submax.
Precisely. The learned trajectory must be physically feasible. It has to respect the hardware limits. Gmax limits how fast you can move in k-space, your velocity, and Zmax limits how quickly you can change direction or speed, your acceleration.
So that stops the AI from designing, say, impossible hairpin turns that the gradient coils just couldn't produce.
Exactly. If you run these optimizations without the physical constraints, the AI often comes up with mathematically optimal but physically impossible waveforms that demand infinite acceleration. The constraints are crucial to ensure the learned trajectory is actually usable on a real scanner and hardware-friendly.
Okay, that makes sense. So when they did these experiments comparing AI-learned trajectories with constraints against the traditional fixed patterns like Cartesian or spiral, what did they find? Did it actually work better?
The results reported in the sources are, frankly, quite striking. The learned trajectories consistently produce significantly better image quality measured by metrics like peak signal-to-noise ratio, PSNR, and structural similarity index, SM, compared to the standard fixed patterns at the same acceleration factor, i.e., same scan time reduction.
So faster scans with better quality.
Mm-hmm.
And did the AI adapt the path depending on what was being scanned?
Yes, this was another key finding. The AI demonstrated remarkable context awareness. It learned different optimal trajectories for different anatomies.
How so? Like, what was the difference for a knee versus a brain scan?
For the knee, which has lots of fine details, sharp edges between cartilage, bone, ligaments requiring good high-frequency information, the learned trajectory tended to spend more time sampling the outer regions of K-space.
Okay, prioritizing resolution.
Right. But for the brain, where the image is often dominated by the large-scale contrast differences between gray matter and white matter, the low-frequency information the AI learned to prioritize denser sampling near the center of K-space.
Wow. So it didn't just find one better path, it found a better path for that specific anatomy and the likely diagnostic goal.
Exactly. It learned to characterize the different spatial frequency content of different anatomies and adapt its sampling accordingly.
And this better sampling strategy, did it show up in things like the point spread function?
It did. The PSFs resulting from the learned trajectories typically showed reduced side lobes and a more uniform, less structured noise pattern compared to the PSFs from fixed undersampling patterns like radial or Cartesian.
Which translates to fewer artifacts in the final image.
Fewer aliasing and structural artifacts, yes. A cleaner, more accurate image reconstructed from the same amount of data acquired in the same short time. It really feels like a potential paradigm shift towards personalized, optimized MRI physics designed on the fly. #tag outro.
Wow. This has been a really deep dive.
Right.
We've gone from, the basic quantum spin of a single proton all the way through the Larmor equation, gradient fields, this whole abstract concept of K-space.
Which is really the frequency map of our own bodies.
Yeah. And understanding K-space, it really reveals those elegant but also kind of brutal trade-offs that are just inherent in MRI, doesn't it? Speed versus SNR.
Resolution versus noise amplification. The constant fight against decay and field imperfections. It used to be the assumption that the human designer, the cartographer, had to pick the path beforehand, balancing all these.
But I think the most powerful takeaway, for me at least, is that resilience of K-space you mentioned.
Yeah.
That holographic nature. The fact that the whole image is sort of encoded everywhere.
Means we can actually afford to miss quite large chunks of data, which is what enables not just the older compressed sensing, but now this even more sophisticated AI-driven trajectory planning.
And the technology is catching up too, right?
Yeah.
Real-time reconstruction using powerful parallel processing FPGAs.
Absolutely. That's changing the game. We're moving away from needing rigid, pre-planned patterns. Now, potentially, Any data point we acquire, as long as we know its precise vec-t location, can contribute to refining the image essentially in real time.
So, okay, let's end this deep dive with maybe a provocative thought, building on that incredible power of AI optimization we just discussed. If a complex medical image, like, say, the human thorax, is already so complex in K-space that even expert humans rely entirely on a computer to reconstruct it.
What does it really mean for the future of diagnostics, for our standard of care, when we start relying entirely on a potentially black box system like a neural ODE to choose the acquisition path itself? A path optimized for computational efficiency, perhaps, but maybe opaque to human intuition or physical understanding.
The AI is making the best trade-offs under that tyranny of time, presumably.
Presumably. But that question of trust in the efficiency, but also the potential biases or lack of generalizability baked into these AI design physics, that seems like the next huge challenge we need to grapple with in medical imaging.